A simple example which demonstrates this idea of a sum over all paths is outlined by Richard Feynman in his book QED, The Strange Theory of Light and Matter. Feynman begins with how to calculate the probability that a particular event will happen. This is done by saying that the probability of an event occurring is equal to the square of the length of a vector arrow representing the event, called the probability amplitude. So there's a rule for drawing these probability amplitude vectors. If an event can happen in different ways, we draw a vector arrow for each way and then combine the arrows using vector addition. That is to say, we line them up head to tail and draw a resulting vector arrow from the tail of the first to the head of the last, like so. This final vector is the one that we square the length of to give us the probability of the entire event. Let's apply this to the case of light reflecting from a mirror. When we shine light onto a mirror at an angle relative to the normal, we find that the angle of incidence equals the angle of reflection. So we can write theta I is equal to theta r. Let's suppose we have a light source S here that emits light of just one colour, say red, at a very low intensity, low enough that the source only emits one photon at a time. We place this source above a mirror and then place a detector at point P and a screen between S and P. I'm going to subdivide the mirror up here. Classically, we expect the light to reflect from the middle of the mirror. However, if we forget about the rule of the angles of incidence and reflection being the same, we can imagine infinitely many paths that the photon could take, like so. Let's simplify this a little bit and say that the mirror is a thin strip that is segmented. We shall say that only one path is allowed for each segment, and will work in just the plane containing S and P. Each of these paths is a way in which the event of light going from S to P can happen, therefore each path has one of the associated vector arrows we talked about earlier. Let's imagine that each photon is being timed by an imaginary stopwatch with a watch hand. As this photon travels along a path from A to B, the hand of the stopwatch turns. And stops when the photon reaches point B. The direction of the vector arrow is given by the direction that the stopwatch hand is pointing in at point B. So we are going to construct these vectors for each of our imagined paths. A question here is, how do we know how long to make each of the vectors? As it turns out, we can say that a photon actually has a nearly equal probability of travelling on any of these paths. Hence we can draw each vector as having essentially the same length. However, the time taken for a photon following each path will be different, and so the direction of each vector will be different. To determine the direction of the arrows, we'll draw a plot of how much time it takes for a travelling photon on each path, like so. We now draw the corresponding vectors for each path underneath. We now add these vectors together, placing them head to tail, and we construct a final vector by joining the tail of the first vector to the head of the last vector. What we notice is that the vectors corresponding to the longest paths don't contribute strongly to the magnitude and direction of the final vector v. Instead, it is the paths that reflect in and close to the centre of the mirror that contribute most of the length, as they point in nearly the same direction because their times are nearly the same. We also notice that where the time is minimum, so at the bottom of this curve, these are the paths that mainly contribute to the final vector. This is what leads to the high probability of the photon reflecting off the centre of the mirror, and hence why we say that light travels on a path that minimises the time taken.